So in today's session, we'll be learning about Tendermint, the Byzantine generals problem, what are the requirements of for BFT as a consensus algorithm, its consensus process, benefits of BFT, its use cases, and also we'll be knowing a little bit about transaction life cycle in detail and how transactions are picked up from a mempool. So let's get started. So Tendermint. Tendermint is a Byzantine fault tolerance consensus engine that is mainly used for building blockchain and distributed applications. As Rohit already mentioned, blockchain is a distributed replicated state machine in which a software is being run on different nodes and validator validate for a specific transaction, and the transaction is getting added in the block. So how it is being done in the background, let's understand that. So Tendermint consensus algorithm works as follow. So we all know that in Cosmos we have multiple validators. For each chain we have multiple validators, and all the validators are having different voting power. Mainly it is for decentralization. Like the concentration of voting power is not just in hands of few validators. So we have voting power distributed among various validators. So when a transaction is created, a validator proposes that transaction into a block. And how it is done? So first step is a validator is chosen to propose a new block. The other nodes vote on the proposed block. So now only validator proposing the block doesn't makes the block. All the other nodes, all the other validators need to agree on that specific transaction. Yes, that this transaction is right. This is not malicious and all. And if the majority of nodes vote for the proposed block, it is committed to the blockchain, right? In majority of nodes do not vote for proposed block, the validator is penalized and another validator is chosen to propose a next block. So what does it mean? If majority of nodes doesn't vote for a proposed block, the specific validator which is not proposing or voting or pre-committing or doing anything is penalized, and its staked amount, whichever stake, like for example, if he is validating on Atom or Cosmos network, suppose he has a voting power of 2% or 3%, and he's having stake quantity of around 100k atoms, right? So in that case, some amount of token is being slashed from his stake position, for this misbehavior. So this was like how a block is proposed in general. Now we'll understand the Byzantine's problem, right? So it's a classical problem that asks a group of nodes or a distributed system to agree on a state. And if there are only like if most of the people are agreeing on a specific motion, like yes or no, then only we proceed with the specific, like motion. If the Byzantine in terms of generals problem, if he has to attack and the number of generals that are saying yes we have to attack outnumber the number of generals that are saying we have to retreat, then only the Byzantine general, that in that case only we are going to attack. So to propose or to different approach to solve this problem is to use a consensus algorithm, in which what we do is we do voting, right? So, and how this voting is done in proof of stake, the voting or governance is the main, like what we can say, main feature, which allows Cosmos SDK to be more, what we can say, decentralized. As we have discussed earlier, different validators have different voting power, right? So whenever a proposal is passed, validator is independent to choose, like yes, if he is in favor with the proposal that is going live on the chain, or is he against. So if more than 2/3 of the validators are saying yes we want to like make this proposal happen or pass this proposal, then only the proposal gets passed. So here is a visual representation of how the problem is being approached. If a validator that is sending malicious information and his traitor, so that block is being rejected, that is in terms of general blockchain, not specific to Cosmos SDK or any Cosmos specific chain. That is in general, the block is abandoned and all the transactions are reverted. And whenever a loyal a loyal block is being formed and that is being accepted, so that agreement is being done in through the consensus algorithm of voting that we have already seen in the previous slide. So now we have to see what are the requirements for this BFT algorithm. So the first and the most important thing is replication. So replication, BFT system typically require replication of nodes or replicas to ensure fault tolerance. Multiple replicas are deployed and they collectively reach a consensus on the correct value or decision. So replication helps to tolerate the Byzantine faults by allowing the system to continue functioning correctly, and even some replicas exhibit faulty behavior. So even if some of the validators are misbehaving, but our most of the validators are trustworthy, then our chain or our system will be in a healthy state. So another aspect is network communication. So what do you mean by communication? All the other nodes are able to communicate with each other. Means all the validators are communicating with each other and uh, accepting a state. So BFT algorithms rely on communication among replicas to exchange information and reach consensus, what we call as consensus state. It's crucial to have reliable and secure network communication channels among replicas. So the network should be able to handle message delivery, ensure message integrity, and protect against unauthorized tampering or eavesdropping. Another thing is authentication. We need to authenticate, like if the transaction is genuine or not, right? And the second last thing is fault detection and correction. So BFT algorithms require a means to detect faulty replicas and differentiate them from correct ones. So uh, in what this means, like fault detection and correctness. So we need to monitor, like, yes, if some validators are sending or someone is trying to send faulty transactions, so we are able to identify it and also correct it. Not correct it means correcting the info that is coming from the user, but correct it like in the next transactions or next transactions that are being taken on our chain. And the last one is quorum. VFT algorithms often utilize a voting or agreement mechanism where a certain number of replicas must agree on a value of decision. This is typically achieved through a Byzantine quorum, which we already discussed, that is voting, through voting or governance. And the last one is resilience to attack. BFT systems should be designed with security in mind to withstand various attacks, including cyber attacks, where an adversary creates multiple malicious replicas to disrupt consensus. Techniques such as proof of work, proof of stake, or practical PBFT, what we call, can be employed to mitigate these attacks and ensure overall system resilience. So this was the requirement that are like what are all the requirements needed for BFT. Moving on to next slide is the algorithm. So what we are using is just PBFT. Okay. So PBFT mainly has three phases of its like life cycle. The first one is prepare, then commit. So it requires a trusted leader to initiate a consensus process and uses digital signatures for message authentication. We'll be seeing how signatures are done by initiating a transaction later on this session. So Also, what are its benefits? It has high availability, scalability, security, and also some drawbacks, what we can say as complexity and performance. So for example, I can show you, let me see here. We have our Comdex binary installed in our system. So when we simply click on, go to the binary Comdex and execute it, it says it has various different types of transaction. And what we are mainly dealing with is the transaction type, right? So when we go and do Comdex TX, it has a sub command for different modules which we will be learning like in greater depth in upcoming sessions, but I can like give you a brief introduction of what are these. So if we go to Comdex TX, we have a list of different module and their subcommands. For example, if we go to Vault, Comdex TX Vault, and we have a series of available subcommands that are present in the Vault module. So we have create, we have deposit, we have withdraw, draw, repay, close, and we also have some flags. So for example, if we want to create it, I'm not creating a vault, I'm just showing you that what are the parameters it takes, how the key validation or signature validation is being done. So see, here it accepts 4 arguments. Right now, I haven't given any arguments. So app ID, extended pair vault ID, amount in, amount out, and flags. So here are the flags. So we have a fees from is the user, which through which you are initiating the transaction. You have gas. Also we have chain ID here. We have chain ID, for which chain ID we are initiating the transactions. So we are putting in some random value, one amount in, one u atom, amount out, one ucmst. So if I try to initiate, it will simply ask for invalid amount. Just a second. It takes an amount as directly, not in terms of coin. So okay. So see here it shows error from cannot be empty. So I have to put in a from, like who is initiating this transaction. So simply you can create your own keys, add your own keys, create your own keys, add your own keys, and initiate transactions from them. So simply what you can do is Comdex. I hope you all have Comdex binaries installed by now. So Comdex keys, add some random name. I'll choose my name. So see, a key is created by my name, and here is the key, and here is the seed phrase that I have got. Typically, you should store your seeds very carefully. Like we can have a different session on it, like how to properly store your keys. But for now, here are your keys. You can simply write it somewhere and save it. So I got my address, I got my account imported here. So what I will do, I'll just go to the transaction and see, input my address, not address, simply name will do, from Pratik local. So it failed because right now the chain is not running. I need to use some kind of node and pass in the RPC to get this transaction done. In that case, I have, just a second. I have a system where the chain is running. I can show you the transaction. I'm creating a transaction of lend, for example, from tx lend. So here are the available commands. I'm simply lending a asset into a specific pool. So asset ID, amount, pool ID, app ID, and flags. So I'm simply showing you the transaction and how it works and how is the transaction hash queried, everything, right? So I'll simply put in asset ID 1, or I will simply deposit CMST in pool 1. Okay. Asset ID for CMST is 3, that is configured for this chain. How we can see that is by this comdex q. Here q means query. Asset assets. I know the queries, so I was able to write it perfectly in first time, but you need to query like this comdex q asset and see the available commands. Here you have assets, so it will query all the assets in that are present in the chain. So here we see we have third id 3 for CMST. So what we will do, I will simply lend. Okay, so asset id 3 amount 1 2 3 4 5 6 7 8 UCMST, pool ID 1, app ID is 3, that I know, from cool user, that's my username here, and I've saved it in keyring backend, that I'll discuss later on what is this, and it's present in here, keyring backend test. And we also need to specify the chain ID for which we are initiating the transaction. Will hit, it will see the confirmation that the signature legitimate verification which it asks for is like this: confirm transaction before signing and broadcasting. I hope this is visible. So I'll simply click in Y and click yes. So here is the transaction hash which I got for lending this particular asset in the pool 1, right? So how can I query and get the data in this particular transaction? Simply comdex q and tx. What it does is, see, query tx, and we need to pass in the transaction hash, this one, this particular one. Comdex q tx, this. So right now the transaction failed because out of gas location we need to specify the gas because we tried to initiate the transaction without gas, so the transaction was failed. These are the basic checks which Tendermint checks on its level, so that we are not giving any gas, so the validator is not going to pick it up, or the gas required for this particular transaction is very high, so it is not being able to like validate and go into the pre-commit or the commit state, and it failed. So what we'll do is simply put in the gas filter. What was the gas required? We'll simply copy and paste and simply just improve it, like increase it by some numbers. We'll try to do it again. And now if we see and query it, you can see gas is taken. So we'll put in higher value of gas. We'll simply put in 3. Now query again. So here is all the raw log for that particular transaction, who is the recipient, what is the value, everything is defined in here. Timestamp, what is the transaction which it is hitting, what is the gas wanted and how much the gas is used, what's the height at which the transaction took place. Everything we can query from this transaction hash. So what I was trying to say, like this, in transaction, how the transaction verification or digital signatures are done. That is what we saw just now. Now moving on to next slide. So in consensus process, the first step is proposal. A validator proposes a block containing set of transaction. So here we can see the block number was 85200. So Right now in this machine, only one validator is there because it is for local use only. So in this particular complex chain, the validator proposed a transaction or a block which contained this particular transaction at this particular height. Then there are something called as pre-vote. Validators independently validate the proposed block and broadcast their pre-vote message, and the pre-vote includes in the hash of proposed block the hash which we just saw and queried it. Then we have something called as pre-commit. The validators receive pre-votes from two-thirds of their total voting power. They independently validate the pre-votes and broadcast their pre-commit message. Pre-commit includes the hash of proposed block and pre-votes. And the final or like what we can say the commit stage. Validators receive pre-commits from two-thirds of the total voting power, and they independently validate the pre-commit and move to the commit phase. In the commit phase, validators create a new block. So the new block was created. Now, if we query, we will have blocks that are higher in number than 85200 because multiple blocks has been created after I created or initiated this particular transaction. And the finality. If a block receives two-thirds of the pre-commit, it becomes irreversible and final. Finally ensures that all the honest nodes have agreed on the order and content of transaction. So everyone has agreed that yes, this transaction was correct, and the transaction is finally included in this particular block. You can also see the validators. Let me see. Comdex Q. Sorry. Comdex query export. Just a second. Let's see if we can see. Log count and elevator set. Here it is. What it requires, see, as what I have said, we have only one validator. Here we can see all the details of this particular validator. Its address, its priority, its pub key, its value, its voting power, everything is defined here. We can create a validator also, but that would be a complex and complete new thing that we can discuss on next sessions. But we can also create and add up to this network. Like we can start validating blocks for this particular complex chain that is running on this particular server and have our own validator created with our own set of params. Now moving on to next slide, the benefits. So right now we all know what are the benefits of BFT, fault tolerance, which we have already discussed. Consistency and validity, security, everything is predefined, like the validators, how they are slashed for misbehaving, everything is there. Now moving on to use cases. Also one more thing here, if I hope all, like, I don't know, most of you are not aware, but there's something called as mempool. Whenever transaction, suppose right now we have initiated only one transaction, but there can be multiple users that are trying to do different transaction, whether it be sending, receiving, creating a vault, lending, borrowing, anything in respect to any particular chain. So in a particular block, there can be hundreds of transactions, right? And how they are sequenced. So transaction ordering is something which we are seeing here. So suppose a validator is to supposed to validate this particular block. So the transactions here are in sequence: transaction 1, transaction 2, transaction 3. If the transaction are split across different, now see, what does this mean, split across different nodes, right? So this is completely new thing. So what it tries to say is that there can be multiple validators, right? And we are not sure like which validator is validating this particular block, right? There can be suppose there are A, B, C, and 3 validators, and there are 3 users. we don't know which validator will validate the next block. So now person A is trying to do a transaction using the nodes or RPC of particular what we can say is first validator, right? We have three validators, we have three endpoints. We can use three endpoints to directly commit a message, like do any transaction. So right now we have only one validator. So we are and that is also running in our local environment. So we don't need to pass any specific information. But let me show you how we do it. So see, here is something what we call as node, and here we pass in the RPC. Okay, RPC of a particular validator, rpc.comdex.1. So suppose there are hundreds of validators, and we have hundreds of RPC. So we can use any of the RPC, and the transaction will be going through that particular node or that particular validator. That is clear. So how it is being done? So validator A, two transactions are being hit, and validator B, only one transaction. And if validator B is the proposer, the order might be transaction 3. Validator B is the proposer. So first is this. Then he is including validators A, transaction 1 and transaction 2. Similarly, if validator A is the proposer, the order will be transaction 1, transaction 2, and transaction 3 in order. So this is how the transactions get included in a block. And finally, coming to use cases. So use cases is pretty straightforward. Everything that Cosmos is being used for is directly being like is a use case for Tendermint. For example, it would be NFT or borrowing, lending, minting, or anything. Either it will be Oracle services, anything that is being implemented. But what is being implemented by Cosmos, it has an underlying technology of Tendermint. So that is how it is being used by multiple things like decentralized finance, supply chain management, IoT. So this was a complete summary of Tendermint, how it works, what are validators, how they propose, what is the significance of voting power and governance. So that's it for Tendermint.